So we've got 11.1 vector valued functions here. A vector valued function is a function of the form r of t equals the vector v of t, g of t, h of t. Okay? So you can almost think of a vector valued function as a parametric equation of a line. Okay? This is where f, g, and h are real valued functions. Okay. So let's define like what the domain and range of this vectored value function is. So what is the domain? These are all real numbers t such that r of t is defined. Okay? So whatever value real numbers I can plug into t, where the output r of t is defined. Okay, that's the domain. The range is all possible output vectors r of t. Okay? So that's the domain and range of a vector valued function. So let's just take a graph here, right? And say we have r of t equals, and we'll just talk about in two space, t comma t squared. Okay, this is a vectored valued functions. Now, something to note about vectored valued functions, all vectors start at the origin. Okay, all vectors start at the origin. So if I take a real number, say t equals 2, so when I plug that into my function, r of 2, we have a vector 2 comma 2 squared, which is 4. Okay, so I start at the origin, I go over 2 and up 1, 2, 3, 4. So my vector goes to that point right there. Okay, and if I were to do this for all real numbers, okay, for all real numbers, this is a faster way to write for all real numbers, all right, t, then, and then have my vectors go through the curve that would be plotted out would look like this. Now, instead of having infinitely many vectors drawn out, all starting at the origin and going to all of these places here, what we do is is we graph the set of all these terminal points, okay? And so that's what makes this, quote, curve here. These are all the endpoints, the terminal points of the vectors R of t. So you don't plot all the vectors, you just look at the endpoints, the terminal points of R of t, okay? So that's the idea. All right, so not a real valued function, but a vectored valued function. Okay, domain, all real numbers t such that R of t is defined. So we plug it in, it's defined. R of t is that vector valued function. And the range are all the output vectors R of t. Okay, and then we don't plot those red vectors. We plot the terminal points, those little purple dots that are on your curve there. All right, so let's take an example, okay? Example, R of t equals the vector cosine of t, sine of t, and let's put one more dimension on this, t. And let's plot it for 0 to 2 pi inclusive here, okay? So if you just look at the xy plane, these first two components here, then what do you have? You have cosine t, comma sine t, okay? And this plots the unit circle, okay? Unit circle going around the origin like that with a radius 1 unit for the unit circle, right? Okay, so any point on this curve is divided by that angle theta there. That's cosine theta, comma sine theta, okay, for any point. All right, now, but this third component here does what? So we're going from 0, a height of 0 in the z direction, up to a height of 2 pi. So instead of it being just on the plane, okay, and just stuck on that circle, what's happening is we're going to be going upwards, okay? We're going to be going up as we traverse around that circle path, okay? All right, so let's see if we can plot this thing, okay? So let's do my best to draw this out. So we've got x, y, z. So this still works for the right-hand rule, okay? So if we start, where do we start at? Well, when t is equal to 0, okay, cosine is 0, comma sine of 0, comma 0. So that's 1, comma 0, comma 0. So start right here at 1, okay? Now, what happens? We go, as your t increases, it's turning us around the circle like this. So we're going to go in this direction like that. Okay, so as we rotate around, say we get to t equal pi over 2. Okay, so that's going to be this angle right here going to the y-axis now. That gets us cosine pi over 2, comma sine pi over 2, comma, pi over 2, which gets 0, 1, pi over 2. So now our x is 0, so we're on the y-axis. Our y is 1, so we're out, okay, to 1. And then our z value is up a little bit, so maybe the dot is somewhere about here, okay? All right, so this vector is 0, 1, pi over 2, okay? So I'll write this down, 1, 0, 0 for that point. And so it's working its way up. So that first quarter turn of the circle is right there, and we're kind of like projecting down onto it. It looks like a circle if you're not taking into account the rise in the z values as we go up. As it rotates its way around at pi, what's going to happen? The cosine is going to go to -1, okay? The sine is going to go to 0, and then the height, how high up we are, is going to be at pi now. So this is -1, 0, pi here. So we're spiraling upwards, okay? And then my last dot, working my way up around like this. Here, once I make that full turn in, I'm back to the same x and y value component, but I'm 2 pi units above. I'm 2 pi units above where I had started, if that kind of makes sense 3D wise. Now, technically with the vector valued function, like we talked about a second ago, there's all these vectors, okay? So the vector there, a vector here, a vector there, a vector there, a vector there, infinitely many vectors that form this vector valued function. But we don't plot all of these infinitely many vectors in here, okay? We don't plot these vectors. What we do is we only look at their terminal points, okay? And that's what we plot. All right, so it looks very familiar, but it's not a real valued function. It's a vector valued function where we're just plotting those terminal points on the vector, okay? So let's talk about displacement for a second. What is displacement? Displacement, d of r of t from t equal t naught to t equal t1 is equal to what? It's d, which is r of t1 minus r of t naught for t naught less than t1. Okay? So what is the displacement for the problem we just did here? Okay? The displacement, this is the different, it's different than the distance traveled. Okay? Displacement is different than distance traveled. All we're looking at, okay, for d is r of t1 minus r of t naught. So in this scenario, t started at 0 and ended at 2 pi. So we need to figure out r of 2 pi minus r of 0. And we actually calculated that a second ago. R of 0 is 1, 0, 0, and r of 2 pi is 1, 0, 2 pi. So when we do this, we get 1, 0, 2 pi minus 1, 0, 0, which gets me 0, 0, 2 pi. Okay? No big deal there. All right. So what does that look like? Okay? That's the vector that goes from here straight up 2 pi units. Doesn't go left or right or up or sideways, north, south, east, or west. It just goes straight up 2 pi units from this point up to this point here. Okay? That's the displacement. But remember, displacement, this is different than how far we travel. Because how far we traveled was a lot longer than 2 pi units, wasn't it? We traveled starting here and made our way around a sphere, a circle, not a sphere, sorry, up to that point right there. Okay, so that's different. That's a different length than just going that straight distance straight up. Okay, it's like walking up a spiral staircase versus going up an elevator. All right, those are two different distances traveled. Okay, the next one I want to talk about is the average rate of change on T0 to T1. Okay, so the average rate of change. So the average rate of change, this is equal to R of T1 minus R of T0 over T1 minus T0. Okay, so how do I calculate this for the problem if we just keep sticking with the same one? Let's do from A to B, so this once again from 0 to 2 pi. So this is R of 2 pi minus R of 0 over 2 pi minus 0 for this scenario. And what do we get for the average rate of change? We get, well, 1, 0, 2 pi minus 1, 0, 0 over 2 pi, which we found to be 0, 0, 2 pi divided by 2 pi, which works out to 0, 0, 1. Okay, that is the average rate of change on 0 to 2 pi for the function, the vector valued function, r of t equals cosine t, comma sine t, comma t. All right, and so that's going to conclude section 11.1.